Okay, class. I don't see anybody in the chat room right now, but I'm going to go ahead and get started. We're going to cover 3 sections today, and we're going to do things with integers. Oh, hi, Abby. Can you hear me? Can you hear Abby? Okay, good. All right, we're going to go over 3 sections today. 2 of them are on integers, and then the last section, 1.9, is on making graphs of information. So let's go ahead and get started. So 1.6, again, introduces integers. And there's a box in your book here. I didn't write the page number down, but it's in section 1.6 about negative numbers and absolute value. And so I just want to point out, your book looks at a negative number, like -5, with the sign, which is either positive or negative, and then the size. And if we look at a number line, the size tells us how many units we move along the number line, and the sign tells us the direction. So when negative numbers move to the left, positive numbers move to the right. Opposites are numbers that have the same sign, same size rather, but opposite signs. So -5 and 5 are opposites. And then all of the numbers with their opposites form the set of numbers called integers. And when we draw a number line, we generally use integers on it. And also absolute value. So the absolute value of a number is the size of the number. How many units is it from 0? So -5 is 5 units from 0. +5 is 5 units from 0. So let's take a look at some example problems. What is the opposite of -8? If you want to answer them, Abby, that's fine, or I can just click and show the answers. But the opposite of -8, remember, it would have the opposite sign, so it would be 8, right? And then how about the absolute value of -11? So again, we're talking about the distance from 0, right? What is the sign of 24 and the size? So I didn't mention before, if there's no sign in front of 24, we assume that it's positive, right? Because normally, yeah, and 24. Yeah, normally if it's positive, we don't write the positive in front of it. Okay, how about this one? Read and simplify. So we've got a negative. So basically what we're saying here, we take the opposite of -6. And negative of -6 gives us, the opposite of -6 is 6, right? Oh, I'm sorry. Oh, how did that get messed up? You're right, this should be 6. I don't know why that's, hold on a second, let me get my little tool here. It should be +6, sorry. There we go. And then read and simplify this one. These are in opposite opposite places, that's why it's messed up. Okay, so again, this is the absolute value. How do we read it? It's the opposite of the absolute value of -6, correct. And I have my 6's in the wrong spot here. This is -6. Yeah, they're in different places. How bizarre. This is the absolute value of -6, which is, as you said, 6. No, it should be -6. Yes, these are reversed. Sorry, I'll fix that. For some reason, when I uploaded my material, these two got switched, so I have to fix those. But now they're right. The following examples don't use negative numbers, but each one has a positive or negative meaning. So we want to determine whether we would use a positive or negative number. So for instance, 100 feet below sea level. Would that have a negative or a positive connotation to it? So if we're below sea level, that would make us think that we're talking about a positive or negative number. So below sea level generally means, yeah, negative, absolutely. And then how about, oh, hi, Thomas. I'm sorry. I didn't notice you had come in. How about this one? If we're $500 in the black. Now, this would be positive. If you read through in the book, actually, sometimes in spreadsheets, especially when we show numerical information, financial information, you'll hear people say, I'm in the red. Red generally means negative. Black generally means positive. How about this one? -30 degrees. What does that mean? It means 30 degrees. Notice the negative sign is so it is going to be below 0. Right? All right, and how about, I think I have another one. A poll has a plus or minus 3% margin of error. So sometimes you see this, especially with political polls. So what it means is that there's a range of values. so that are likely by taking whatever the estimate was, adding and subtracting 3%. So for instance, if we did a poll and let's say 50%, well, let's make it more interesting. Let's say 36% of the people said they would vote for, I don't know where you guys live, but there's a mayoral election coming up in St. Petersburg. So let's say we did a poll and 36% of the people that we sampled said they're going to vote for Rick Kreisman. So with that margin of error, the true estimate is somewhere between 33% up to 39%. So that's what a margin of error means. If you ever see that in an article or something, it means take whatever the estimate was that they came up with and then add and subtract 3%. So that's a nice application with negative numbers. This one's an application from the book, and they actually have you start reading graphs here. Write a sentence to explain Lily Lake's enrollment. So let's take a look at Lily Lake. Lily Lake is right here. What's happening to Lily Lake's enrollment? And this is what they're expecting to happen from 2013 to 2018. Do we expect it to go up or to go down? We're expecting it to go... Yeah, we're expecting it to go down, right, by about 12%. You're absolutely right. Yep. So that's another application here. We wrote drop, so we didn't put a negative in front of it, but we're actually looking for a decrease here. So notice down here, these are all negative percent changes. So nice application. You'll see some things in your homework like that. All right, so let's keep working with the integers now. So let's talk about operations with integers. And you may remember these rules. If you're adding two numbers with the same sign, you simply add the sizes and keep the sign. So if we wanted to add negative 15 and negative 40, we add 15 plus 40 and get 55, and we keep the sign. If we're adding numbers with different signs, we subtract the larger number minus the smaller number using the sizes here. And then we keep the sign of the number with the larger size. So if we wanted to add negative 22 and 30, we subtract and get 8, and we keep the sign of the larger number based on size, which is positive. All right, so let's try a couple here. They're asking you to do it without a calculator, but let's take a look and see. Or you could do it on a number line also. So here we're adding two numbers with the same sign. So what do? We add the sizes, keep the sign. Anybody want to try that one? So what are we going to get when we add negative 58 and negative 18? And we're going to get almost negative 76. And then how about the same numbers now, but both positive? So we're going to get 76 again, but it's positive. Okay. How about this one? Now I'm keeping the same numbers, and notice I'm mixing up the signs on you. How about this one? Okay, 40, Thomas. Is this one positive or negative 40 on this one? So we subtract. So 58 minus 18 does give us 40, but is it going to be positive? No, it's going to be negative, right? Because this is the larger size. This is going to be negative 40. Okay, Thomas, does that make sense? You see that? Because this number has the larger size, so we keep that sign on the answer. And then how about this one? We're going to subtract again. This time 58 is the larger size, so it's going to become positive 40. All right. Oh, you were looking at the second one. Okay, that's fine. Actually, and here's something else which is nice to do. Some students like to do this. We can change subtraction into addition. So instead of subtracting, we can add the opposite. So for instance, if we have negative 5 minus 10, we can rewrite this as negative 5 plus the opposite of 10, which is negative 10. And we can get negative 15. So this is another way that you could work the subtraction problems as addition. You can do whatever is more comfortable for you. All right, let's try these three here. Anybody want to try this one? So negative 120 minus 7. Yep, negative 127. How about this one? Anybody want to try that one? Yep, everybody got that. 43, good. And then how about the last one? Yep, negative 60, good. All right, here's a couple more. Now, how about this one? Now remember, we can change subtraction into addition. So this will become plus 12. So the answer here is the same as the last one. It's negative 60 again. Uh-oh, how about this one? Fractions. Oh no. First thing I would do on this one is change it into adding the opposite. So to do that, I'm going to change this into an addition, and since this is negative, it's going to become positive. But what do I need to do when I'm going to add two fractions? I have to have the same denominator, don't I? Yeah, we need the same denominator, which here is going to be what? 12, isn't it? So, see if I can jot this with my trusty little mouse here. So I've got negative 2/3. And what do I need to multiply this by in order to get 12 in the denominator? I need to multiply by 4 over 4, right? 4 over 4. And then here I need to multiply 1/4 by 3 over 3. Whoops. The mouse doesn't work real great on this whiteboard. Okay. So, now hold on a second. What do I get here? I've got, the first one's negative, isn't it? Negative 8 over 12. And then I have plus 3 over 12. Now be careful. I've got a positive and a negative number here. So what am I going to do? Negative 8 plus 3 gives me what? Negative 5 over 12. So notice the difference, Thomas, because the first fraction is still negative, so when I go to add them, I'm going to actually subtract, okay? So it's negative 5 over 12. And my little answer is going to pop up there. All right, let's see. Multiplying and dividing. Okay. When we're going to multiply, we simply multiply or divide the sizes, and then we have some rules about the signs. Remember, if the signs are the same when we're multiplying or dividing, we always get a positive result. If we're multiplying or dividing two numbers with different signs, we always get a negative result. So let's try a couple. Oh, these are a bit harder, actually. Again, you need the same denominator on these. I'm going to let you work on these because I didn't put all the intermediate steps up. The LCD on this one is 8 times 17, which is 136. And when you change the subtraction into adding, they're going to both be negative. This one, simply multiply the numerators, multiply the denominators, simplify if you can, and notice the answer is going to be positive. Let's simplify before we multiply, because we notice that 4 goes into 8 how many times? 2, right? So what are we going to get? We're going to have positive 3 over 34. And then remember, when we divide, remember we talked about this last week, when we're dividing fractions, we change it into multiplying by the reciprocal of the second number. So let's see if I can jot this over here real quick before we look at the answer. This is going to become 15 over 2 times, we have a negative, we don't want to forget that, 11 over 30. And again, I like to cross out common factors, so 15 goes into 30 twice. So what am I going to get for an answer? Negative 11 over 4. Okay, so this time we're pulling together the fraction rules and also the integer sign numbers rules. So again, we did a lot of things with integers, but if you notice at the end there, we were also working with fractions, so the same rules kind of apply. And then just to finish up this section, real numbers are all the numbers that can be represented on the number line. And they could be fractions, they can be decimals, they can be irrational numbers. All those things can be shown on a number line. So we have counting numbers, which start at 1, and those are integers starting at 1. We have whole numbers, which start at 0. We have, remember, the integers, the whole numbers and their opposites. Rationals can be written as the quotient of two integers, and then we have irrationals, which cannot be written as the quotient of two integers, things like square root of 5, pi. Those are all real numbers. There are imaginary numbers, which are not numbers that can be shown on a number line. We're not going to cover those in this book, but there is another whole group of numbers called imaginary or complex numbers. But we're focused on real numbers in this course. All right, and then the last section, I think, which is kind of a fun one, is making and interpreting graphs. So when graphs are used to display data, and when we move to the next cycle, you'll see in statistics we use a lot of graphs. And you want to display the information so people can really understand what the information tells you. We can have quantitative data, which is numerical data, things like heights and weights and age and grade point average and things like that. These all have units that go with them. And then we also have what are called qualitative or categorical information, things like car names, the color of your car, political affiliation, race, ethnicity, gender. Those are all data that put the information or the things we measured into groups. So a pie chart is a good way to show this kind of information, where it shows a comparison between a part and the whole. Now, your book goes through great detail about how to create a pie chart. Honestly, most people today would use something like Excel. They wouldn't do a pie chart by hand. But basically what your pie chart does, it takes the pie, the circle, and divides it up to show relative sizes of categories. So for instance, this is how the teacher determines the final grade in her class. The tests are 60%, the homework is 15%, and the quizzes are 25%. And again, I wouldn't worry about this figuring out how many degrees would be in each angle, because generally nowadays people use technology. There's a tech tip over here. What I'd like you to think about is what the graphs tell you. So let's take an example here. So Ian attends a company-sponsored workshop that's designed to increase employee efficiency. His task is to create a pie chart showing how he uses his 8 hours at work on an average day so that he can better use his time. So here's how his day is distributed. 1.5 hours every day at meetings, 2.5 hours on the computer, 1 hour for calls, a half an hour for breaks, 1 hour for lunch, and then 1.5 hours for off tasks. So the total here is 8 hours. So when he goes to the pie chart, here's the data. Here's how it turns out. So basically what happened in the percents, let's just go back for a second. To find the percent in each category, here I would take 1.5 and divide it by 8, multiplied by 100, and that would give me the 19% you see here. Likewise for the computer, the off task, and so forth. And when we add the percents up, we hopefully should get 100%. So the pie chart now tells me he spends the largest chunk of his time on computers, an equal amount on meetings and off tasks. Lunch and calls are the same percent, and then breaks is the smallest percent. So nice display of his average workday. Another way you can use qualitative or categorical data is with a bar graph. And the bars are can be horizontal or vertical, and generally they don't touch when we do a bar graph. And if we put them in order from smallest or highest to lowest, it's called a Pareto chart. And again, these are helpful when we want to compare part-to-part comparisons. So for instance, here's a list of the top 10 gas prices by state in the United States. Obviously, this is quite a long time ago. And we want to put those into a bar chart as a Pareto. So who is the most expensive? Notice, let's go back for a second. When we're looking at the data, it may not jump out at us that California, this is alphabetical, California is the highest price. And after that, it's kind of hard for me to see who's next. But if I put them in a Pareto chart, I can see very nicely California is most expensive, then Alaska, Nevada, etc., all the way down to Wisconsin. So a nice display of the data. Notice also here along the y-axis, there's this little squiggle line, and that tells us that our line does not belong, it doesn't start at 0. We started at 2, so which kind of inflates the difference among the groups. But that's a nice bar graph. And again, here's how to create a bar graph. And again, generally most people use technology, and in a bar graph, generally the bars do not touch. And then we can also do a line graph, where we have a series of connected ordered paired data points. And because this data has an implied order, we can connect the dots. And these are often used to show data over time. And I've got an example from your book. It accompanies over-the-counter and prescription drugs. There's a pamphlet of information for the consumer. And in this particular one, we're looking at the concentration of, this is Tylenol, in the body, measured in micrograms per milliliter of blood. So let's take a look at the graph. And the horizontal axis represents the number of hours since we took the medication. And the y-axis is going to show us, actually I'm going to have two different types of medications. the level of the medication. So here's the graph. So we have an adult liquid and we also have extra strength. They're both the same dose, 1,000 milligrams. And we start here, we take it here, swallow it. And then what happens with the liquid? The liquid goes up, actually goes a bit higher than the extra strength. And then we see as time goes by, the level falls off. And here's the extra strength, it goes up, and then it falls off. And then they're going to ask you some questions about the graph. Write the ordered pair for the point indicated, should say, by the arrow, so the point right here. So basically your origin would be here, and so your x would go over here, so you would go over 2, and then up to about, anybody want to try that one? 212, yeah, 2,12. So in 2 hours with the extra strength, we're at a level of about 12 micrograms per milliliter. Good. And let's take another question. Use the shape of the graph. I'm sorry, this shifted. Use the shape of the graph to describe what happens to the concentration of medication over 8 hours and how a second dose is needed. Let me look at my notes to see what that says. Is needed after 4 to 6 hours. So what happens quickly in the first hour? What happens? It goes up pretty quickly, right? Either one in the first hour. And then about hour number 4, we're really starting to fall off pretty quickly. And then at hour 6, we're way down here to 3 micrograms. So that's probably why we say we get a second dose after 4 to 6 hours. And you can see that in both cases. Let me see what other question they ask you about this one. When do the two formulations result in the same concentration of acetaminophen in the bloodstream? So let's see. It looks like it's hour 5. Yeah, 5, 6, pretty much out here, right? Yeah, probably from hour 5 onward. They're pretty much the same concentration. Good. I got one more. What would be your choice? This is what the question asks. What would be your choice for pain reliever? Would you take the liquid or the tablet? What do you think? Yeah, the liquid seems to peak quicker, doesn't it? It seems to go up higher, faster. Yeah, so the liquid looks better. And then I think I have one more question. The liquid dose is listed as 500 milligrams per 15 milliliters. That means in 500 milligrams is equivalent, there is 500 milligrams of acetaminophen for every 15 ml. If 15 ml is equivalent to 1 tablespoon, how much do you have to take? How many tablespoons in order to get that 1,000? How many tablespoons would we have to take? Yeah, so 1 tablespoon has 15 mLs, which is 500 milligrams. So in order to get 1,000, Abby's right, we'd have to take 2 tablespoons. So kind of like taking 2 pills. Because Tylenol generally I think is about 500 milligrams per pill. So when it's liquid, they put it in a tablespoon. So you have to take 2 tablespoons. All right, and then one last thing from your book. And this just talks about how to make a line graph. So when you're making a line graph, you want to look at the range of the values for what you're going to put on X, the range of what you're going to put on Y, and that will help you figure out your scale. And then you simply plot these, or each ordered pairs, 1, 1, 2, 4, 3, 20, 7, 100, etc. And then those are the points that are plotted here on the graph. And this is a problem about a flu outbreak. All right, so that's what I had to go over this week. Nobody sent me questions, so I didn't pull in anything from last week. Anybody have any questions on any of the material? So this week you're doing the sign numbers, and then you're doing the graphs in section 1.9. Okay, Abby's good. Thomas, and the other student, I'm sorry, I just see your student number, but I don't know your name. So Thomas is good. You're welcome. And student 2360787, any questions? Okay, I'm going to assume, oh, there's other students, I think. Hold on a second. I didn't scroll all the way down. Oh, Alicia's there. Alicia, any questions? Sorry, I didn't see your name. The window doesn't show all of them at one time. She's good. Okay. Okay, if everybody's good, I'm going to go ahead and sign off. And again, we'll pick up next week. I don't know the sections. I don't have it in front of me. Oh, here it is. Next week we do 1.10, 1.11, and 1.12. All right. So everybody have a great week. Okay. We'll chat again next Monday.